Hello everyone. So welcome to this live interactive session for week 3 of the course Introductory Field Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I am a Prime Minister's Research Fellow working at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. So this is the outline of the course that has been taught in week 3, which starts with the basic concepts of folds and folding mechanisms. Then comes the classification of folds, then superposed folding mechanisms, followed by folding and superposed deformation in Ghatshila, and folding and superposition of fold in Tetuldanga, a small outcrop in Ghatshila. So this is the information for the live interactive session. We hold these live sessions for the 4 week of the course, and this is the 3rd week. And this is today is 9th August 2025, and this is the time for joining the course. And this is also the Google Meet link to join the live sessions. So about today's live session, so a brief discussion about what we learned in week 3. So in week 3, basically we started with how to study and interpret a folded structure, identifying the anatomical features of a fold like hinge, limb, inflection points, extrador surface, intrador surface, etc. Outcrop scale features of a fold and how we generally identify them as in the form of antiform, synform or anticline and syncline, etc. And then identifying the fold axis, which is of course an imaginary axis which defines the relation between the limb and the hinge and the axial plane of the fold. So identifying the fold axis, geometric and structural importance of a fold axis, like determination of a fold axis in a regional fold, and then geometric and structural classifications of folds in terms of their opening angle, in terms of the interlimb angle, and the deep of the folds, plunge amount of the fold axis, and the orientation of the axial plane. So that is how we carry out the geometric and structural classifications of folds. Then comes concepts of multi-phase deformation and superposition of cylindrical and non-cylindrical folds. And then of course the most important part for identifying different phases of deformation through Ramsey's classification of folds, outcrop scale features of superposed folds, that is whether it is type 0 or type 1, type 2 or type 3, and identifying the different phases of deformation from superposed folding. And then of course how the knowledge of superposition of deformation can be applied to understand and interpret the superposed deformation in regional scale, that is the overall region of Ghatshila that we carried out through lithostructural mapping of at different outcrops by observing different small scale features like crenulations and folding of S1 surfaces, and then refolding of the S2 surfaces and generating F2, whether F2 and F1 are parallel or whether F2 and F1 are perpendicular. And that is how in different regions we identified whether it is a type 1 interference or whether it is a type 3 interference. So these kind of things that we generally carry out from large scale field work in a very large region, and then from we interpret how these different phases of deformations are related to each other, and most importantly which one is the fast phase of deformation and which are the following phases of deformation. That is what we generally carry out in regional scale. And then of course superposed deformation in outcrop scale, and actually how these features do look like in a very high competency contrast rock that are generally being exposed in the Tehuldanga, that is a very special outcrop and has been displayed in detail in the week 3's lecture videos. So topics for today's discussion will be mostly about interaction about the week 3 course content and answering any doubts if any, then solving conceptual questions related to the week 3 contents, and finally summary and conclusion. So this was the overview of what we are going to discuss for today's live session. Now let us begin about some conceptual problems that I have designed carefully to match with the content of week 3, in where we mostly learned about ductile deformation, specifically related to folding, and I have gathered some and curated some problems related to fold and folding mechanisms. So the first question is, find the direction of the hinge of the regional endiform. So this is the hypothetical image of a cross section that we observe in a field, and these are the traces of the bedding planes, these blue lines, and the dashed lines are the traces of the axial plane, and then we have small angle alpha and obtuse angle theta, and within the bedding plane surfaces like here and here, there is also some second order folds which we observe, and from here there are four options given. That is, the hinge of the regional antiform will be towards the opening of theta, towards the opening of 90° minus theta, towards the opening of alpha, and towards the opening of 90° minus alpha. So from these four options you have to select one, which is probably the correct answer for, in this case, determining the hinge of the regional antiform. So this is a outcrop scale feature or a part of the fold which has been exposed in the field. You do not know where the hinge of the regional fold, you just got an outcrop, but from that you have to interpret whether we are observing the correct section or not, and if so, then what will be the probable direction of the hinge line. So let me pause for a minute and give you some time to think, and then we will discuss what will be the right answer. Any guess? Okay, so let us start with the discussion. So first of all, larger folds commonly have small scale folds, specifically in their limbs and the crest or the hinge. And these second order folds are generally known as parasitic folds. And these parasitic folds, they form during flexure of layered rock where slip occurs between rock layers, right? and this is a mechanism which is commonly known as flexural slip. So most of the field asymmetric folds that we observe in the field are generally formed due to this mechanism. So majority of the asymmetric folds in nature, they form through flexural slip. And the second order folds have asymmetries related to the sense of slip on each limb, and they are called S and Z fold. So the sense of slip is like this. You can easily guess. For a compression following this direction, the general sense of slip for this fold will be in this manner, this fashion. And first of all, answering the question, the correct option will be option C, which is towards the opening of alpha. That means in this direction, this will be the probable direction for the hinge line. Hinge of the regional fold. Right. Now, how do we get a sense of what is happening? So this mechanism of understanding the sense of rotation and displacement or the slip in these kind of parasitic folds, it is known as the vargence. Right? And the difference between S and Z folds lies in their sense of rotation. How we are classifying which one is the S fold and which one is the Z fold, and the sense of rotation is commonly termed as vargence. It is generally estimated through the long to short to long limb of the second order folds and the sense of the rotation. Right. So if I have a bedding plane like this, for a layer that has generally been folded, and if I get a fold like this, parasitic fold, so this will be the long limb, this will be the short limb, and then again this will be the long limb. So long to short to long. So this is the general pattern how we recognize these folds. So this makes a shape of Z, and that is why we call them as Z fold. And in case of S fold, long to short to long. Right. So this is how the S fold is generally estimated. So this is again the trace of the bedding plane. And this is generally makes the shape of S, and this is S fold. This is the Z fold. In case of Z folds, the sense of rotation is clockwise, and in case of S folds, the sense of rotation is counterclockwise. Right. So now this is generally for second order parasitic folds which are present, But in case of cleavage bedding relation, so if I just have axial planar cleavage, right? So in case of cleavage bedding relation, the opening angle, right, of the opening direction of the acute angle of the acute angle between the cleavage bedding intersection will be the direction of the closure of the fold. Closure, or which can, in other words, we can say the hinge part of the fold. So that is how we can see that opening direction of the acute angle means this is the acute angle alpha, this is the acute angle alpha. So this opens towards this direction. Now if you just follow, this is the bedding plane, this is the axial plane, and this is again the bedding plane. So the acute angle between the intersection of the bedding plane and the axial plane, and this acute angle, the direction along which this acute angle is actually opening, that will be the direction for the hinge line of the fold. However, there is a note of caution in this case. I mean, if I just use this method for interpreting the closure of the fold, I should have to follow a note of caution. And that being the sense of fold rotation displacement will change if a fold is viewed from the opposite side. From the opposite direction. That means Z fold will appear as S fold. Right. Hence, it is necessary to indicate the direction in which the observations are made. right? And it is better to choose a section or to observe, to record these vergence when the fold is, when the fold is viewed from the down plunge direction. So if possible, the fold should be viewed down plunge. Okay, so this is the, I mean, this is how one should approach the divergence in case of understanding folds in a regional scale. Okay, so let us move on to the next question. Which one of the following statements regarding cleavage refraction is true? Option A, buckling instability alone produces cleavage refraction. Option B, flexural slip alone cannot produce cleavage refraction. Option C, flattening plane of the local strain ellipsoid remains parallel to the bulk strain ellipsoid. And option D, cleavage refraction is a non-penetrative event. So since in the previous week we already learned about what is cleavage refraction, and in this week's content we learned a lot about um, how folding works and even some concepts regarding cleavage fanning. So I think it is better to relate folding mechanisms and cleavage refraction, then we can have a thorough understanding how these things happen and how then they can be made useful in interpreting the regional scale deformation. So these are the four options, and I will pause for another minute to let you think. And if you come up with an answer, you can always unmute yourself and answer. Otherwise, after a minute, we will eventually discuss what will be the correct answer for this question. So the correct answer in this case, first of all, buckling instability alone produces cleavage refraction is a completely false statement, because uh, cleavage refraction primarily originates from the viscosity contrast, right? And it cannot alone produce the diffraction of cleavage planes, axial planar cleavage, unless there is some asymmetry introduced during folding, right? So in a similar sense, cleavage diffraction is a non-penetrative event is also a false answer, because this is a continuous process. I mean, it is present throughout the volume of the rock, because it is a region of deformation, ductile deformation. And generally for ductile deformation, we do not observe non-penetrative structures. So in this case, cleavage diffraction is definitely not a non-penetrative event. It is definitely a penetrative structure. So option D is also discarded. Now, talking about option B and C, it is true that flexural slip alone cannot produce cleavage diffraction, and it is the most viable option for these for amongst these four given options. So option B is the correct. So because flexural slip is an important component to produce cleavage diffraction. However, along with flexural slip, one also requires viscosity contrast between the adjacent layers, to produce cleavage diffraction. And since flexural slip activates because of the relative displacement between layers, relative displacement and heterogeneous shortening, and shearing between between the different layers. Therefore, um, the flattening plane of the local strain ellipsoid rotates differently between different layers. And that is why the flattening plane of the local and the bulk strain ellipsoid are not parallel. Okay, so this is how we um, approach towards understanding the relation between flexural slip and cleavage refraction. So this was question number 2. Now let us head on towards question number 3, which says that in a fold, if the curvature of the inner arc is lower than the curvature of the outer arc, the deep isogons, option A, converge towards the inner arc, option B, diverge towards the inner arc, option C, either converge or diverge, and option D, remain parallel. So again, if you have learned about the Ramsay's classification of fold in terms of the deep isogon, the layer thickness, right, then you can probably answer this question, because this is the classification for I mean, these are the major parameters for classifying folds according to Ramsay's classification. But nonetheless, I will also pause for a minute to let you think, and if you come up with an answer, you can always answer it, and if not, then I will uh, discuss what will be the correct answer for this question through a uh, proper graphical plot between the parameters that I will be describing. Okay, so first of all, let us define what is deep isogon. So the image deep isogon is the imaginary line that connects the points of equal depth right between the extrados and the intrados. So if I follow the description, this kind of fold we are talking about. So this is the intrados and this is the extrados. So the curvature of the extrados is greater than the curvature of the intrados. Okay. So if I draw the hinge line and then select different points, say for example at this point, this is deep alpha and this is also deep alpha, and then we selectively choose different points along the limb of the fold in both directions, and then if we just plot the change in the, or simply just plot, so this if this is point 0 and this will be the distance from the hinge, so we can term these two parameters alpha deep amount and d sub h is the distance from the hinge. Right, then if we just plot a graph between alpha and dh, we would probably see graphs like this. So this will be for the extrados and this will be for the intrados. Right, so if this is the case, therefore to maintain the equal deep amount, the deep isogon must have to the deep isogon has to diverge. Deep isogons have to diverge away from the axial plane towards the inner arc. Right, so the first deep isogon, obviously this one, second one with this one, this one, this one, like this. Because the deep along the extrados changes much rapidly than the deep amount in the intrados, right? So that is how we, or I should plot probably the del A, that means del alpha, that means the change in the deep amount, right? So going away from the hinge line, the deep amount changes very rapidly in case of extrados than the intrados. Therefore, to match with the equal deep, match with the points having equal deep, the deep isogon has to diverge away from the axial plane. So this is the axial plane, right? So the deep isogons has to I have to diverge away from the axial plane. So diverge towards the inner arc. So starting from outer arc to inner arc, we see that the deep isogons are getting diverged, right? So option B is the correct answer for this question. Okay, let us move on to the next question. An open fold may appear to be isoclinal when viewed in a section, option A, at a low angle to the fold axis, option B, at 45 degrees to the fold axis, option C, perpendicular to the fold axis, and option D, parallel to the axial plane. Again, so this is somewhat easier than the previous three questions. And if you just can imagine about what is an open fold, and how we can cut them to get a slice in which the limbs will be actually parallel. So that is what isoclinal fold means. I mean, you will have two limbs which has the same attitude. That's it. So if you can get that kind of apparent section along which the fold appears like that, then obviously it will be an isoclinal fold. So if anyone wants to answer the correct option for this question, please go ahead. Um, please unmute you. Please mute yourself, so it will be easier to continue the discussion. Thank you. Yeah. So now, if we just follow what is an open fold, that means it has a very low dipping limbs, right? So the open fold might look like this actually. Now, for a fold like this, so if we have to get, so if I just get the profile plane as the outcrop in a section, in a 2D section basically, so the profile plane would look like this if I just get a 2D section. This is definitely not an isoclinal fold, right? What an isoclinal fold would be is something like this: traces of the limbs which are essentially parallel to each other. Right, so this is how one should get the section, the trace of an isoclinal fold. So if we cut an open fold at a 45 degree with respect to the hinge plane, the fold axis. So if I just consider the fold axis to be non-plunging, so if this is the fold axis, then the profile plane or the section plane which I am cutting across should make an angle of 45 degree like this, right? So if we cut something like this following this plane, then we will get um, even more opening towards more than what would seem in the profile plane. That means the interlimb angle would appear to be larger than what we would generally observe in the profile plane. Right? So definitely that would not give us the isoclinal fold. If we cut any section perpendicular to the fold axis, like this one, the profile plane, or any plane that goes like this, that is the axial plane, then also we will just see just section of the bedding plane, the traces of the bedding plane, right? So we won't be able to see the two limbs. Only if we cut almost parallel to the fold axis like this, or at a very low angle to the fold axis like this. So some sections probably around 2 to 5 degrees with respect to the fold axis like this one. Then we can get the traces only from the hinge part. And since the beds are very shallow dipping, that means a section which is almost subparallel to the fold axis would give us the traces of the bedding planes at both of the limbs, which would appear almost parallel since these limbs are very shallow dipping and they are dipping away from each other. So in this case, if we just cut a section across the fold at a very low angle to the fold axis, then only it is possible to get an apparent section of the fold which would look like a trace of the isoclinal fold. Because in isoclinal fold, the bedding planes at both the limbs, they have the same attitude, right? So this would provide an apparent section where an open fold might be viewed as an isocline fold, right? So in this case, option A is the correct answer, which means that the open fold has to have a section cut at a very low angle with respect to the fold axis to get an apparent section that matches with an isoclinal fold. Okay, so moving on to the next question, which says that which of the following statements regarding transposition of deformation is true? Option A, transposition foliation is an indication of superposed folding. Option B, stratigraphic information is retained in case of transposition structures. Option C, transposition foliation develops parallel to the axial plane of tight folds. And option D, fold closure can be well identified in transposition structures. So if you are not familiar with the concept of transposition, then we will discuss about what transposition means, and from there we can interpret what would be the correct answer from these four options. But if you just know what the transposition is, then I would pause for a minute to give you some time to think about the right answer for this question. Okay, so defining transposition. So a process, transposition is a process where a pre-existing layering like bedding or foliation is folded and rotated in to such an extent that its original orientation and structure is obscured and overprinted. The resulting structure appears as a new layering often subparallel to the later stage of foliation. Right. So if this is the definition of transposition, which means that if you have a folded layer and these are the previous axial planar cleavage. Now if we compress this entire thing in different mode of deformation, the folds may appear very tightly like this, and the existing foliations would become so much squeezed and compressed that they should become a single unit, and eventually the fold would look like this. So this would eventually take a shape like this through thorough deformation and continuous compression and shearing, and eventually what would happen, the initial stresses of the S1 cleavages, these, if these are the S1 cleavages, they will be completely obscured. That means we will not be able to see a such thing, and a new foliation plane will be overprinted over on this structure, and the new foliation like this would become a spaced foliation, and these kind of folds that they actually remain between the S2 or the second generation of the foliation planes, and they completely get rid of their initial structure and their orientation, whatever that might be, and they should appear as a completely different deformation signature when they are viewed in a proper section, right? So in very highly deformed terrain where there are alternate um, tight rock and soft rock and hard rock and soft, so if there are some alternation between alternating layering between sandstone and mudstone and all those things like that, and because of continuous metamorphism, mineral reaction, weakening of the phases, eventually these kind of folds, which are initially open folds or gentle folds or even isoclinal folds, they got squeezed in a manner such that they appear as rootless folds. So this term is very important for this kind of folds. If we observe these kind of folds in very highly deformed terrain, such as if you just visit Rajasthan and Shingbum Craton, there are plenty of examples where we observe um, rootless folds. So they are very early generation folds that were later being modified due to overprinting relation of later phases of deformation, and eventually we produce these kind of structures which are also known as intrafolial folds. So if we just follow what we are discussing, then it is easy for us to say that option C is, these options are right, because transposition foliation develops parallel to the axial plane of the tight folds. So generally, if these folds are very tight in nature, then they will have a tendency to be at least parallel or subparallel to the initial foliation of the tight folds, and eventually they will be squeezed hard enough to get rid of the initial foliations of or S1, and they will appear as rootless folds between spaced S2 cleavages. Right. So this is what we know as transposition. Okay, so let us move on to the next question. Which of the following condition describes a reclined fold? Option A, plunge of the fold axis is equal to its rake. Option B, plunge of the fold axis is equal to the apparent dip of the limbs. Option C, plunge of the fold axis is equal to the dip of the axial plane. And option D, plunge of the fold axis is parallel to the strike of the axial plane. Okay, so if we follow what is a reclined fold, so reclined fold is a neutral fold. So what are neutral folds? One is recumbent fold, option 2 reclined fold, option 3 is vertical folds. So if I just draw what is a recumbent fold, I would get a stereonet like this, where this is the fold axis, and the axial plane is basically the periphery, right? Because it is horizontal. So this is recumbent. And if I just draw a vertical fold, so if I just move the fold axis to 90 degrees, and then I have the axial plane. So this is where the fold axis will lie, right? So just shift the fold axis from 0 degree to 90 degree, but in doing so you are also shifting, also changing the dip of the axial plane, and in such a manner that for recumbent fold we see that the fold axis is non-plunging, and so does and that means the fold axis is horizontal, and so does the axial plane. But then for vertical folds, the fold axis is 90 degrees, and so does the dip of the axial plane. So from this we get a definition of neutral fold is like plunge of the fold axis is equal to the dip of the axial plane. That is how that is how a neutral fold is defined. If the plunge of the fold axis becomes equal to the dip of the axial plane, then it is a neutral fold. And for a neutral fold, the trend of fold axis is equal to the dip direction of the axial plane. That means if we draw a stereonet, if this is the axial plane, then if this is the dip of the axial plane, this is the dip direction, this will be the fold axis, and they would have a same trend and dip direction for the plunge and the dip amount of the axial plane. So option C is correct, because for a reclined fold we need plunge of the fold axis to be equal to the dip of the axial plane. And for also an extra information is that for a neutral fold, like for a reclined fold, sorry, no, so for a neutral fold the trend of the fold axis is equal to the dip of the axial dip direction of the axial plane. That would be defined as the reclined fold, right? So this is the general definition for a neutral fold, and specifically talking about reclined fold, you just also need to mention that the plunge, the trend and the dip direction, or trend of the fold axis and the dip direction of the axial plane, they are also the same, and that is how we should get the definition of a reclined fold. So option C is the correct answer. Now moving on to the next question. High angle intersection between bed and foliation indicates option A, limb of a recumbent fold, option B, limb of a tight fold, Option C, hinge of a fold. Option D, limb of an open fold. So if we follow, sorry, what a fold look like. So if this is the axial plane, then these will be the traces of the axial plane, right? So parallel to the axial plane. So if we go away from the, so if I just mark these intersection angles alpha, and if we just consider the fold to be symmetric, this is how it should appear. This is 90 degrees, right? So the angle between the cleavage bedding intersection decreases away from the distance from the axial plane. So the highest angle of intersection will appear at the hinge of the fold. In this case, alpha is the intersection angle between obviously acute between the cleavage plane and the bedding plane. Right? So this is how we define the relation between the interaction between cleavage and bedding planes, and obviously at the hinge zone the angle is at its highest, which is 90 degree, and therefore option C is the correct answer. Okay, so moving on to the next question, which says that interlimb angle and shape of a fold is best studied in a section parallel to the plunge of the fold axis, section containing the pole of the bedding planes, section parallel to the pole of the axial plane, and option D, none of the above. So there are four options. Which of the given options describes the best shape of a fold, in particular the interlimb angle for a fold? So if we have a fold, then section parallel to the plunge of the fold axis means, if this is the fold axis, then plunge means if this is the fold axis, which means this is plunging in a direction like this, whatever may be the plunge amount, then a section cut parallel to this line would definitely look like this. And if we see this, again we will see the cleavage bedding intersection, right? So this is obviously not the correct answer. Now comes the pole section containing the pole of the bedding plane. So pole means if this is a plane, then the vertical line drawn from that plane orthogonal to that plane will be the pole, right? So pole means an orthogonal relationship between a plane and a line. Therefore the bedding plane should contain the poles like this, right? So a section means containing the poles means obviously this section, right? So this will be the section which is parallel to the pole to the bedding planes, right? So therefore the section containing the pole of the bedding planes will be the profile plane, right? So this will be the profile plane of the fold, and as we know profile plane is perpendicular to the fold axis. orthogonal to the fold axis. So this is the best section for studying the interleave angle. So option B is the correct answer. That is, section containing the pole of the bedding planes will be the appropriate section for studying the interleave angle and the shape of the fold. That means whether it is an open, gentle, tight, isoclinal, whatever. Right? Okay. Now let us move on to the next question, which is in Ramsey's fold classification, class 2 fold is characterized by option A, core converging deep isogons, option B, parallel deep isogons, option C, core divergent deep isogons, and option D, uniformly inclined deep isogons. So I will pause for another minute to think that which will be the right answer. Then, of course, we will discuss this question. Okay, so Ramsey's classification uh, includes curvature of the extrados and the intrados, and the layer thickness. So if we just plot a graph, curvature of the extrados and curvature of the intrados, right? So CE is the curvature of the extrados, and Ci is the curvature of the intrados. Then of course for this kind of graph we will always have a 1:1 line. Now for 1:1 line it divides the entire graph area into two prominent parts. First is a part where the curvature of the intrados is greater than curvature of the extrados. Or we can just write in notations. So number one will be Ci, curvature of the intrados is greater than the curvature of the extrados. These kind of folds are called class 1 folds. And these kind of folds have the inner arc having higher curvature than the outer arc. So in a previous question we already attempted to see that in case of a fold where the inner arc has less curvature than the outer arc, in that case the deep isogons tend to diverge away from the axial plane towards the inner arc, right? So this will be the exactly opposite scenario where the inner arc has higher curvature than the outer arc. So for folds falling with in this kind of category, that is the class 1 folds, will obviously have convergent deep isogons, right? So these kind of folds are also called as convergent folds. Option 2 will be this 1:1 line, which is also class 2 folds, which means Ci is equal to Ca. And since the curvature of the inner arc and the curvature of the outer arc are both same, it is safe to assume that in this case the deep isogons will remain parallel to each other, right? So that is why these kind of folds are called parallel folds. Not exactly parallel fold. These are called similar folds. Sorry. And then comes a region where curvature of the inner arc is less than the curvature of the curvature of the intrados is less than the curvature of the extrados, and these kind of folds are called class 3 folds. And this is the one we already discussed. Obviously this is a divergent fold. For class 1, there can be again three types. One is thick fold, which means thickness increases with DH, you know, DH means the distance from the axial plane or distance from the hinge, right? Uh, Parallel fold, where thickness is constant. With DH. And the last one is thin fold, which is exactly opposite to the fast kind of folds, right? So these are known as 1A, 1B and 1C category of folds that belong to class 1 kind of folds. So this is how, based on the curvature and the thickness of the fold layers, Ramsay's classification can be simplified for understanding what is class 1, what is class 2 and what is class 3. And if you just follow the discussion, it is easy to say that in Ramsay's classification, class 2 folds is characterized by obviously parallel deep isoforms because it lies on the 1:1 line. Right? Okay, let us move on to the next question. Joints perpendicular to the fold axis, which are a common feature in orogenic belts, are commonly known as option A, columnar joints, release joints, extension joints, and cross joints. Say, for example, we have a folded layer. Like this. So during exhumation, so if a folded structure is exhumed upwards, obviously there will be release of stresses and that will create tensile stresses. So tensile stresses, so because during a compression regime the folds were obviously compressed like this to get this kind of shape. Now these stresses are removed and during exhibition they are released from their state of stress. If that happens, to maintain the equilibrium, the points within the material, they will obviously exert a tensile stress like this when they are exhumed. So obviously there will be four directions or two perpendicular directions along which the tensile stresses due to exhumation will work. So along this direction, if this is the direction of exhumation, a kind of joint plane will develop like this. Fracture planes, joint planes would develop like this. So following this direction, and following this direction, a joint plane will be formed perpendicular to the previous set of joints like this. So these kind of joint sets which are perpendicular to each other observed on folded surfaces, they are commonly referred to as cross joints. So in an orogenic belt, due to differences in the stresses, folded structures particularly they would definitely develop cross joints. So option D is the correct answer in this case. Moving on to the next question. During layer parallel compression, two layers of stiffness ratio of 1.5 with thicknesses of 2 centimeter and 4 centimeter respectively produces buccal folds in a rock. The ratio of their wavelengths will be so in order to determine what will be the ratio of their wavelengths, we have to apply the Biot's formula, which generally takes into account the viscosity contrast of the competent and the incompetent layer and their amplitude and thickness. And generally we write the Biot's formula.
Sir, how
Yes,
long class will be continue?
just another 5 minutes.
Okay, sir. Thank you.
So the Biot's formula is L by H, that is the wavelength by the amplitude or thickness of the layers, is expressed as 2 pi cube into root over of mu1 by 6 mu2. So mu1 and mu2 is the ratio of the stiffness of the materials. Competent and incompetent layer. So the value is generally given, I mean in this case the value is 1.5. So the L by H ratio, it easily boils down to 1.5 over 6 because 6 is in the denominator, and therefore we generally reduce 2 pi cube times half, that means just pi cube. Now H1 is 2 centimeter and H2 is 4 centimeters, and since the L by H ratio is nearly constant, then we can write that L1 by H1 is equal to L2 by H2. Therefore L1 by L2 will be H1 over H2, right? Which means 2 by 4 or half. So the ratio of their wavelengths can be expressed as 1:2 or half. So option D is the correct answer. Question number 12 says, in a zone of superposed folding, poles to the bedding plane shows a great circle distribution. For such a case, the fold axis related to the first generation of folding will be option A, also be also be distributed along the same great circle girdle. Option B, be distributed on a great circle girdle orthogonal to the bedding plane girdle. Option C, shows a cluster around the pole to the bedding plane girdle. And option D, shows a small circle distribution around the pole to the bedding plane girdle. So the poles to the bedding plane girdle means these are how the poles to the bedding plane are distributed, and they would generally form a great circle. Right? So poles to the bedding plane follow a great circle, which means that the fold, the fold surface is uniform, and hence it is cylindrical, right? So if this fold is cylindrical and the poles to the bedding plane, they follow along a great circle, then definitely this plane is the profile plane of the fold. And if this is the profile plane of the fold, that means pole to the profile plane would automatically be a region where the fold axis will be expressed, right? So this is the fold axis. Now, since there are a lot of points on the bedding plane, therefore taking an average data, we will find a cluster uh, which is the pole to this great circle. Therefore, option C will be the correct answer, which says that it will show a cluster around the pole to the bedding plane girdle. Right? So this is how the fold axis related to the first generation of folding will be expressed. So this is FA1, the first generation fold axis. Will show a cluster. Okay. Finally, to the last question. A set of cylindrical upright folds superposed by another set of non-coaxial folds. The axis of the superposed folds at any spot is determined by option A, fold dihedral angle of the first set of folds, option B, fold dihedral angle of the axial planes of the two sets of the folds, option C, intersection of axial planes of the two sets of the fold, and option D, intersection of the limb of the first fold and the axial plane of the latter folds. Now, superposition of cylindrical folds, cylindrical upright folds, and another set of non-coaxial fold will lead to type 2 superposition. In case of type 2 superposition, the fold axis 1 is also folded to produce the second generation fold axis. Therefore, just by studying the fold axis of the two folds and the dihedral angles, it will not be easier to identify. Uh, it is not easy to determine the fold axis just by studying the dihedral angles and the limb of the intersection of the first fold and the axial plane of the later folds. Therefore, it requires a section where the two sets of axial planes intersect. From there, the FA2 can be determined. So that is why option C is the correct answer in this case, because intersection of the axial planes of the two sets of folds will give us the axis of the superposed folds at any spot along the polydeformed tenon, right? Okay, so we have just completed our today's discussion on folds and folding mechanisms, that is the ductile deformation we observed in the field. And in the next and the final session of this discussion, we will be talking about brittle deformation, ductile shear zones, and practical aspects of strain measurements in the field. Until then, see you in the next Saturday this time for the last interactive session. So thank you for joining today's session. Goodbye.